describe day 3. See if I can get this. There we go. Okay. I've got the shade pulled down right. Okay, so not near as long as day 1, but a little longer than day 2 as far as notes go. Individuals. Also called experimental units. Bless you. If they're human, then they're called subjects. So a little terminology there. Next, we're going to look at 3 principles of statistical design of experiments. When they're principles, that usually means they're pretty important. The first one being control. Control is the overall effort to minimize variability in the way experimental units are obtained and treated. The overall effort to minimize variability. In the way experimental units are obtained. Oops. Comma there. And treated. If you've been through a science class, you'll want to know that control does not equal control group. They're not the same thing. The next thing is replication. Replication is the idea that we use enough individuals to reduce chance variation. experiment, and one of the individuals happens to be, or would happen to be under normal circumstances, an outlier, you may not know that with only three data points, right? So you have to make sure that you're choosing enough that you can identify those outliers in a group. So replication has a lot to do with just group size in general. And the last one is randomization. Randomization is simply the rule used to assign individuals to treatments. This one's an important one. Well, they're all important, of course. The other day we talked about smoking and doing an experiment where I talked about maybe splitting this half of the class, and I said, you guys all be smokers, and this half of the class, you guys all be non-smokers. I'm going to pay you guys to not smoke. I'm going to give you guys all the cigarettes you want to smoke, right? Is that a random selection? To just split the room into two? No, it's not at all. And here's why. In my non-smoking section, I might have a group of 4 or 5 or 6 of you that inadvertently got sat together, or maybe you chose to sit together because you all hang out smoking after school, right? And so I've got closet smokers in my non-smoking group because of splitting half and half in such a very chunk, here's one half and here's the other half. So I would have to do a good experiment to try to control something like that. I would assign everybody a number or put everybody's name in a hat, mix it up, and then I would randomly choose my smoking group, and then whatever's left would be my non-smoking group. So hopefully I wouldn't get too many of those closet smokers in my non-smoking group, because it'd be like, yes, you're gonna pay me not to smoke, and I'm gonna smoke anyway, right? So does that make sense about randomization? That it's absolutely required. Okay, next thing, statistical significance. Statistical significance is an observed effect so large that it would rarely occur by chance. An observed effect so large it would rarely occur by chance. That's sort of the whole kind of idea, really. I mean, if I'm studying something, I'm looking for statistical significance. And I hate to pound on the poor smokers and lung cancer folks, but there's a statistically significant increase in the incidence of lung cancer for people who smoke. There it is, statistical significance, and it's not proof that any one person's going to get lung cancer, but it's evidence that you're a whole lot more likely to if you're a smoker versus not. Okay, I'm going to try to pound a little less on the poor smoking and lung cancer bit as much as I can in my future, but for now, you guys are going to be like, so what'd you learn in class today? Not to smoke. I'm going to go smoke a cigarette just because I was told not to smoke. Okay, completely randomized design. I'm going to talk about two design types. Completely randomized being one, which is, I think, reasonably self-descriptive. It says when all individuals are allocated at random among all treatments. So let's say I'm comparing a new drug to an old drug, and I get a group of subjects, and I would then randomly choose from that group a sample, and then randomly choose which drug those people got. So randomization is important for the choice of the person or the individual. It's also important that the treatment itself be administered at random. I don't mean that it's random each time. It'd be like, okay, I randomly chose that John's going to take the old drug, and I have randomly chose that Ian is going to take the new drug, right? It doesn't mean that you would swap that at any point. You would maintain those positions. The last one that we're going to talk about today anyway is block design. Block design a group of subjects or individuals, I'm going to change that term, a group of individuals because it may not be human, known before the experiment to be similar in some way, known before the experiment to be similar in some way, that is expected to systematically affect the response to the treatments. So let's say we've developed a new pain reliever, and let's say it's closely related to an old pain reliever, maybe aspirin per se. It's closely related, but different, we think, enough that it's maybe going to have a different effect. But perhaps we know that aspirin is more effective on females than it is on males. I don't know if that's true. I'm just making this up. So it's just me posing a particular problem. Then when we do our test, we might consider blocking with our new drug. We might consider blocking males and females so that we're looking at a randomly selected group of females and a randomly selected group of males, probably with the same sort of numbers of selection, so that when we get done with our results, we can say, here's what we found about the females, and here's what we found out about the males. Because it's a pretty well documented fact that, at least in some cases, females and males react differently to the same drug. Maybe not entirely, but there are different effects. Our biology is a little bit different. So we would, a gender block would be something that is certainly used fairly regularly. So you block to control the variables that might influence the response. You randomize to control the unknown variables. Block to control the variables that might influence the response. You randomize to control the unknown variables. So in my example here a minute ago with the aspirin and the new drug, the new pain relieving drug, what if we didn't block male and female? What variable would we be losing control on if we just took a random sample of males and females and tried the drug on all of them? What's that? Maybe not so much age. Gender, right? And age can come into play too, certainly. How we metabolize things as young people, or, well, you guys, as opposed to old people. I don't think of myself as old. I think I'm still only 25, but just so you know. That's going to be different. So, or it can be different. Right. So yeah, we wouldn't be able to designate or decide if there was a difference between the male reaction and the female reaction, when in fact there might be. So blocking is important when necessary. All right, let's look at a couple problems. There are a fair number of problems today. You don't need to write me a book answering these things. Just get an answer down, and we'll go with that.